Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a fascinating paper, Robust Agents Learn Causal World Models. Quite a mouthful, but the implications are huge.
Huge is an understatement. This, to me, feels like a significant step towards true AGI. The idea that agents can learn not just to predict what will happen, but to understand why it happens. That's the holy grail, right?
I'm a little more cautious, Otto. Robust is doing a lot of work in that title. We've seen so many AI systems that perform beautifully in the lab and then completely fall apart when faced with real-world complexity. I'm always asking, does this really scale?
I agree with both of you. Actually, the potential is there, absolutely, but scaling is the key. I think the current deep learning approaches, while impressive, are fundamentally brute force. This paper, though, gets me thinking about spatiotemporal reasoning.
Okay, let's unpack that a little. For those of our listeners who aren't steeped in the jargon, what is a causal world model? What does it mean for an agent to learn one?
Essentially, it's an internal representation of the world that includes not just what things are, but how they relate to each other causally. So, not just if I push this button, the light comes on, but pushing this button causes the light to come on. That understanding of causality allows for much more robust prediction and planning in new situations.
Right? But how is that causality represented? That's the crucial question. Is it just a complex statistical correlation learned through deep learning? Or is there something more structured, more symbolic going on under the hood?
Exactly. Think about it like this. A toddler learns that dropping a spoon causes it to fall. They don't just see the correlation a million times. They start to understand gravity, force, and the spatial relationships involved. That's spatiotemporal reasoning. Can these agents do that? Or are they just really good at predicting spoon falling events based on a massive data set?
That's a great point. This gets to the heart of my own interest. How can we map the structured representations used in the brain, neural pathways, hierarchical encoding, onto the kinds of representations used in these AI systems? The brain is really good at learning causal models. We should be taking notes.
And I think deep learning is taking notes in a way. It's learning these complex statistical relationships, and with enough data, those relationships start to approximate true causality. I think what this paper shows is that we're on the right track. More data, better architectures, and we'll get there.
I'm not convinced that just throwing more data at the problem is the answer. It's like trying to build a skyscraper out of sand. You might get something tall, but it's not going to be structurally sound. We need a better foundation, something more like steel girders, a symbolic framework that can encode prior knowledge and allow for genuine reasoning.
I think it's somewhere in between, maybe. The brain doesn't work just with symbolic logic. It's a messy, parallel system. But it does seem to have these incredible abilities to translate between different coordinate representations. Think about reaching for a cup. Your brain is translating visual information from your eyes into motor commands for your arm, all in real time. That's the kind of flexibility we need in AGI.
That resonates with me. I'm intrigued by the potential for incorporating predictive coding principles from neuroscience into these architectures. The brain is constantly predicting what's going to happen next, and then updating its internal model based on the prediction error. That's active inference, and it seems like a powerful way to learn causal relationships.
Exactly. And that's what these robust agents are doing in essence. They're building an internal model of the world and using it to predict the consequences of their actions. The more accurate the model, the more robust the agent.
But how do we know it's an accurate model? How do we quantify robustness? Right now, we have metrics for accuracy and classification tasks, but what about an agent's understanding of causality? How do we measure its ability to predict the effects of interventions?
That's a really important question. And I think the answer lies in looking at how well the agent can generalize to new situations. Can it take what it's learned in one environment and apply it to another, even if the details are different? That requires a deeper understanding of the underlying causal structure, not just a memorization of patterns.
This reminds me of some work on language models. They're incredibly good at generating text that sounds coherent, but do they actually understand what they're saying? They can mimic grammatical rules, but do they grasp the underlying meaning?
Well, the paper touches on that actually. It talks about how linguistic generalizations aren't necessarily rigid rules, but more like statistical patterns. And that's what these language models are picking up on. They're not memorizing grammar books. They're learning the statistical relationships between words and phrases from massive amounts of text.
And that's precisely the problem. They're learning superficial patterns without any real understanding. They can generate grammatically correct sentences that are completely nonsensical. That's not intelligence. That's just sophisticated pattern matching.
I think it's a bit harsh to say they have no understanding. They're clearly capturing something about the structure of language. But I agree that it's not the same kind of understanding that a human has. We have a much richer understanding of context, of nuance, of the underlying meaning.
So, how do we bridge that gap? How do we build language models that have a deeper understanding of meaning? I wonder if combining neuro-inspired techniques with reinforcement learning could be the answer. If we can directly model the brain's learning processes, rather than just mimicking surface-level patterns, maybe we can create models that are capable of better generalization and adaptability.
That's an interesting idea, and I think reinforcement learning is definitely a promising avenue. It allows agents to learn through trial and error, to discover the causal relationships between their actions and the world around them.
But reinforcement learning still relies on a reward function, and that reward function has to be carefully designed. If the reward function is poorly designed, the agent can learn to exploit it in unexpected ways. We've seen that happen time and time again.
Right. That's where the spatiotemporal aspect comes in. The reward function needs to take into account not just the immediate outcome of an action, but also its long-term consequences in space and time. Think about chess. A good chess player isn't just thinking about the next move. They're thinking about the position of the pieces on the board several moves ahead.
So, let's bring this back to the paper. What are the key takeaways for our listeners? What should scientists and researchers be focusing on next?
For me, the key takeaway is that learning causal world models is a crucial step towards AGI. We need to continue developing better architectures and training methods that allow agents to learn these models from data. And we need to focus on scalability. How can we ensure that these models can generalize to more complex real-world situations?
I think we need to shift our focus away from purely data-driven approaches and start incorporating more symbolic reasoning into our AI systems. We need to find ways to encode prior knowledge and allow agents to reason about the world in a more structured, interpretable way. Neuro-symbolic approaches seem like a promising direction.
I think we need to focus on spatiotemporal reasoning. We need to develop algorithms that can translate between different coordinate representations and reason about the world in a flexible, context-dependent way. That's the key to building truly robust and generalizable AI systems.
And from my perspective, we need to look more closely at the brain. We need to understand how the brain learns causal relationships and how it represents knowledge. We need to translate those insights into computational models that can be used to build more intelligent machines. I am most interested in mathematical ways to model the hierarchical causal structures found in the brain and translate them into algorithms.
And to add to that, I think we need better metrics for evaluating the causal understanding of AI systems. We need to move beyond simple accuracy measures and develop metrics that can assess an agent's ability to predict the effects of interventions and generalize to new situations.
Yes, and we need to be more critical of the claims being made about AI systems. We need to demand more transparency and interpretability. We need to understand why an AI system is making a particular decision, not just what decision it's making.
Absolutely. It's not enough to build a system that works. We need to understand how it works. And that requires a multidisciplinary approach, bringing together insights from neuroscience, computer science, mathematics, and philosophy.
Well, that's all the time we have for today. Thank you all for this fascinating discussion. And thank you to our listeners for tuning in to Cognitive Spirals. We hope you'll join us next time as we continue to explore the mysteries of the mind and the potential of artificial intelligence.
Thanks for having me. This was great.
My pleasure. Always a good conversation.
Indeed, thanks for having me.